Okay, section 3.3 is going to introduce another visual representation of data, and this one's very useful. This one is used a lot in stock trading because you can quickly see the low, the mean, the high of a stock price throughout the day. In stocks, it's called a candlestick plot. They turn it vertically, so instead of horizontally like this, they'll turn it like this. And then you can see how these candlesticks will go up and down throughout the day. But it's pretty simple. So what we have here is it identifies the minimum value of your data. It identifies what we call Q1 or quartile 1. And so if we call it quartiles, that just means that we split our data into 25% chunks. So 25% of your data is below quartile 1. And then we have Q2, which is also called the median. And so again, that would be another 25% between quartile 1 and quartile 2. Then we have Q3, would be this bar here. So again, another 25% between Q2 and Q3. And then we have the maximum value. And then that's the last 25%. And these are called whiskers. And then this box, if you look at it, it also represents 50% of the data. So 50% of your data will fall between quartile 1 and quartile 3. This will often also be called a 5-number summary. 5-number summary, because we get in it, we get from it 5 things: the minimum, quartile 1, the median, which is quartile 2, quartile 3, and then the max. And oftentimes those 5 things are all we really need to know about our data set to make decisions based on it. Okay, so for this first one, it just says identify these things. The minimum height is 152. Oh, these are heights of males in centimeters. That's what this data represents. The first quartile, Q1, that's the first bar, 167.1. The second quartile, Q2, or the median, is this middle bar, 171.4. Q3, 180.4. And the maximum height in centimeters is 195. So if you have the plot already done for you, it's pretty simple. You just pull these values right from it. Again, that's called a box plot. Okay. 22 is a different idea, but might be one of the most useful ideas in all of stat. And that is the idea of normalizing the data. So oftentimes we don't want to worry about units. So I can talk about mean and maximums and minimums of heights, but I might run into problems if I have to think about centimeters or inches or meters, right? These units can get cumbersome. So we turn things into what we call a z-score. And a z-score does not have units. So now I have one number that can represent any unit, and it makes it extremely simple to compare things because all I have to do is look at how big the number is. If the number is big, that tells me something. If the number is small or negative, that tells me something as well. So to calculate a z-score, it's equal to your x value, so some piece of data, minus the mean of your data values, divided by the standard deviation s. We will use this formula over and over and over again, and it will become like second nature for us. Very simple to calculate. Here's how it translates to the normal curve. We have our bell-shaped curve. Right in the center is x bar. So you replace x with x bar, and it would be x bar minus x bar, which is 0. 0 divided by anything is 0. So the center of this curve is now 0. So these are now z-scores in the x-axis. And then one tick mark, if you remember, that was x bar plus 1s. So if I subtract x bar from that, I'm left with just 1s divided by s would be 1. Then this is 2, and this is 3. If we go to the negative side, it was x bar minus an s. The x bars cancel. I'm left with minus s over s, minus 1, minus 2, minus 3. If we think about units here, if we had our heights in centimeters, this would be centimeters minus centimeters, which is centimeters. But standard deviation, we discovered last class, is also the same units as your data. So this would be in centimeters. You have centimeters on top, centimeters on bottom. They cancel. And so you have no units. And just like before, we're going to say anything above a z-score of 2 is significantly high, and anything below minus 2 is significantly low. So that's the theory we need. Let's look at this problem. It says, if your score on your next stats test is converted to a z-score, which of these z-scores would you prefer? Minus 2. Minus 2 for us. So this means this is the exact average score on the test would be a z-score of 0. That's the mean. Anything over here would be high scores on the test. Anything over here would be low scores on the test. So a minus 2, you're way over here. That's your stat test. That means you scored worse than 95% of the people. Probably not where you want to be, right? So that one's out. Minus 1 would be here. That means you scored worse than about 60% of the people. You also don't want to be there. 0 means you scored exactly the mean, the average. We can do better. 1 means you scored better than average in about the top 20% or so. That's pretty good. But the best one would be 2. If you had a z-score of 2 on the test, that means you scored better than 97.5% of the people. So that's the one you want. And so we would say D. Does that make sense? So it's just better and better scores as you move left to right. Okay, 23. A data set lists weights in pounds of plastic discarded by households. The highest weight is 5.32 pounds. The mean of all the weights is x bar equal to 2.216 pounds, and the standard deviation of the weights is 1.008 pounds. What is the difference between the weight of 5.32 and the mean of the weights? So what this question is asking, A is asking, take x, the 5.32, and difference it with x bar. So they're saying x minus x bar, which notice is the numerator of the z-score equation. And so it would be 5.32 pounds minus the mean, 2.216 pounds. And if you subtract those two numbers, you'll get 3.104 pounds. Part B says the difference is blank standard deviations. So they're asking how many standard deviations go into this difference. Asking how many times something goes into a number is division. So they're asking what's x minus x bar, this difference, divided by s. Notice that is exactly what the z-score equation is. So we just need the 3.104 answer we just had, pounds, divided by s, which they gave us to be 1.008 pounds. And this again is where the units cancel. So pounds divided by pounds goes away. Dividing these two numbers on your calculator would give you 3.08. Now notice the next part says, what's the z-score? Well, this right here is exactly the same as the z-score. So these two numbers are the same. So this was z. Now, if we were to plot this on our normal bell curve, notice 3.08 is over here, right? Just to the right of 3. And hopefully you can see that it's clearly in the significantly high bubble. So this weight is significantly high. Any concerns about that one? This sort of subtract and divide pattern is going to be hugely important for us. And then knowing where it lands on the, this is called a standard normal curve when you convert it to z numbers. Let me write that. This is called a standard normal curve. What do you mean by that? Like that? Like the 0, 1, 2, 3? Is that what you're asking? Yes. So the way they ask this question, these two answers will always be the same thing. Yeah, so they're just kind of setting you up. Basically, this problem is to teach you how to break this into chunks. Part A is subtract the two numbers. Part B is divide that answer by this. And then part C is, oh, notice that you just did the z-score calc. Yeah, so they're the same. And it's setting you up to kind of train you how to do this, the order in which you need to do this calculation. Okay, let's look at 24. So now the rest of this section is pretty much just repeating that process of calculating z-scores. So we want to get lots of practice with it. So this one says, the tallest living man at one time had a height of 232 centimeters. The shortest living man at that time had a height of 121.2 centimeters. Heights of men at that time had a mean of 172.32. So notice that's x bar. And a standard deviation of 6.45, that's s. Which of these two men had the height that was more extreme? So we just have to do two z-score calculations, z tall and z short. For Z tall, it's going to be the height of the tall person minus the mean divided by S. For the short person, it's going to be the height of the short person minus the mean divided by S. Notice these two things stay the same. The only thing that changes are these X values. So the tall person was 232 minus the mean, which is 172.32. And I'm not going to write units anymore because we've already proven that units go away. So I don't care about writing centimeters for everything. Divided by this S, which is 6.45. And if you do this, for these numbers, you'll get 9.25. For the short person, you'll take 121.2, his height, minus the same number, so minus 172.32, divided by this same number, 6.45, and that's going to equal negative, because this number is smaller than the mean, and it turns out to be negative 7.93. And we can fill in these blanks. That's the answers for these two. Now the final question is, which one's more extreme? To answer more extreme, you look at the two numbers, you ignore minus signs, and you just ask which number is bigger. So if I throw away this minus sign, I just ask which number is bigger. Clearly 9 is bigger than 7. So the tall person's height is more extreme. This is really just asking which one is further away from the center of the curve. And so obviously the curve centers at 0. This tall person 9 is way out here, and the short person 7 is over here. Clearly this distance is farther away. That's really what it's asking. And we'll learn that if you're like in the third, if you're 3 or higher, that's 99.85%. That means 99.85% of people are shorter than you. That's with a 3. If you're at 9, that's literally, well, he's the tallest person in the world, right? So, billions of people are shorter than this person. 99.99999% of people would be shorter than him. Okay, questions on that one? So that's just using the equation twice and then comparing the numbers and ignoring the minus sign. 25 is similar. We're going to look at ages of Academy Award winners. So we have the age of the winner for Best Actor was 35, and the age of the winner for Best Actress was 54. For all Best Actors, the mean age is 43.4. So we have to break this into, so X bar men is 43.4, and the standard deviation is 8.6. So S of men, you have to kind of delineate men and women here, otherwise you'll get confused. For all Best Actresses, the mean age is 38.2, so X bar women, 38.2. Standard deviation for women is 10.3, so that's S women, 10.3. Find the Z-score of the actor and the actresses. So Z men is X minus X bar men over SM. XM would be the age of the actor we're considering, and this said the best actor was 35. So that's the age of this man, XM. So this would be 35 minus X bar M, the mean age of men, 43.4, divided by standard deviation for men, 8.6. And if you do that, you will get, it's negative because this number is smaller, negative 0.98. For women, very similar calculation, ZW, XW minus X bar W over SW. The age of the woman in question for her award, she was 54. So that's XW. So we have 54 minus X bar W, 38.2, all over SW, 10.3. This number is bigger than that, so this should be positive, and it turns out to be 1.53. Which one's more extreme? 1.53. So just cover up the negative, compare which one's bigger. The 1.53, which was associated with the actress. Good there. Okay. 26. Use the following cell phone airport data speeds in megabits per second from a particular network. Find quartile 3. I never spelled that out. Quartile 3 is what this is. Quartile. So first let's find out how many numbers we have. 1, 2, 3, 4, 5 rows by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. So N, the number of data values, is 5 rows times 10 columns is 50. Now finding quartiles is all about breaking the data into quarter chunks. So first we want to break the data into halves. So half of 50 would be 25. So we want 25 numbers and then the next 25 numbers. Now, this only works if the data is in order from small to big. And we're lucky, this problem would be much, much harder, but they put it in order. So as I go left to right, the numbers get bigger, and then down and bigger and bigger and bigger and bigger. So they're in order. Let me write that. Must be in order. So we just have to count. 25 numbers would be the first 2 columns plus another 5. So you count from left to right. So you get 10 numbers here, another 10, that's 20, 21, 22, 23, 24, 25. So this is the halfway point, which means these two are going to be from 26 to the end will be the next halfway point. Now, if we want to do a 5-number summary, I'm going to show you all the things that they could ask in this question. So you could answer anything they could ask. The first number is your minimum. The last number is your maximum, in order. The middle two, so now this is a little tricky because this is an even number of numbers. So Q2 is the median, but in this case, the median of an even set is the average of the 2 numbers in the middle. So Q2 here would be 20, would be the average of these two, so you'd add them up. 2.4 plus 2.6 divided by 2. And if you do that, you get 2.5. So that's Q2, the exact middle number. Now Q1 is the first quarter. So right now I've got the first half and then the second half and the exact middle. Q1 would be breaking this first half into halves again to make it a quarter. But this is nice now because this is 25 numbers, which is odd. So the exact middle number will be 12 from one side, 12 from the other side. So 12 would be 10 here, plus 2, then the next number. Working backwards, it would be, let me count 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the next number. So this 0.8 is Q1. And then you do the same thing for Q3. So Q3 will be in the middle of this second bracket of numbers. So it's another 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and the next number, 6.9. Let's check that from the other side. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, and then the next number. So that's Q3. And that's all they asked for, but it doesn't hurt to show you how to break the data into all the 5 things they could ask. Minimum, Q1, Q2, Q3, maximum. $27 is pretty much the same, but there's even fewer numbers, so that's nice. But then they're just going to ask us to do one extra thing, and that is make the box plot. But we'll see that it's pretty easy to do so. So we have, these numbers are ratings that women gave men in a speed dating exercise. So it says construct a box plot and the 5-number summary. So first let's find out how many numbers we have. 2, 3, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So n is 20, which is even. So my middle number will be the average of 2 numbers. And in fact, half of n would be 10. So let's count 10 numbers. Well, before I get too far ahead of myself, are these numbers in order from small to big? 1, 1.5. Yeah, so if you look, they're in order. So that's key. They're in order. So now I can just count. Well, I can pick out the easy answers. So here's my minimum, 1.0. Here's my maximum, 6.5. So I can already fill out the first and last answer. 1.0, 6.5. Now I'll count 10. 1, 2, 3, 4, 5, 6, 7, 10. So here's the halfway point. And then this would be the second half. Now Q2 has to be the average of these 2 numbers. So 3 plus 3 divided by 2, which is 3, since they're the same number. So Q2 is 3. That would go right here, the middle box. Now, because this is 10 and 10, those are still even. I have to do the same for Q1, so I have to count 5 now. 1, 2, 3, 4, 5. And then this is one of the middle numbers, and then 1, 2, 3, 4, 5. This is also one of the middle numbers. So Q1 would be the average of these 2, which is 2.5 plus 2.5 divided by 2, which is 5 divided by 2.5, which is 2.5. I mean, I'm showing this just so if your numbers are different, you can get it. But if the numbers are the same, then what's the answer? The same number, right? But I just want to make sure that you see that if these numbers are different, you have to add them and divide by 2. Q1, 2.5. Q3 will be the exact same kind of approach. 5 from this side, 1, 2, 3, 4, 5. So that's one of them. 1, 2, 3, 4, 5. That's the other one. And let's just state the answer this time. It will be 4.0 because they're the same. So 4.0. So we have the 5 numbers. Now the next thing you have to do is just look at your possible answers for the box plot. So let's start with our minimum. The minimum's 1, so that lines up. So this is still a possible answer. This lines up, so that one could work. This one lines up too, so that one could work. This one starts at 0, not 1, so we can throw him out. So D's out of there. Let's go with the maximum. It's actually easier to see the minimum and maximum. So 6.5. So this one goes all the way to 8. So he's now out. This one goes to 6.5, so that could work. This one goes to 8, so it's out. So with just checking 2 numbers, it's got to be B. And if you look, the other ones line up. So Q1 is 2.5. Yep, that works. Median was 3. That works. Q3 was 4. That works. And then 5. Maximum was 6.5. So this one works perfectly. Any confusions there? Okay, let's go to 28. So 28, they want us to build 2 box plots, one for the pulse rate of men and one for the pulse rate of women. And we actually already studied this problem last section. And here's the data values they give us. So they give us 2 tables. Each table has 1, 2, 3, 4, 5, 6, 10 by 4. So each one has 40 values. And here's our issue is that they are not in order. So if they were in order, we could do this problem by hand. But they are not in order. And I'm certainly not expecting you to put 40 numbers, actually 80 numbers in order, smallest to biggest. That would take half the test time, which would be silly. So let me show you how to do this one with the computer. So in this problem, you'll see a little table button. It'll look like this, and you're going to want to click that. Clicking that will load these numbers up. Then in the top right of these numbers, there will be a symbol that looks like this, a window and a window. You'll click that. You'll say open in StatCrunch, which will take these 40 numbers and put them into our StatCrunch program. Then you'll click the graph button. From the graph button, they'll show you a bunch of options. You will select box plot. And then you want to make 2 box plots at once. So you're going to click men's pulse rate, and then you're going to hold down Control key, and you're going to click women's pulse, which will put both of these lists of numbers into the program. Then there's a little box that says you're going to check the box that says draw boxes horizontally. So it defaults to drawing them vertically, which I said is useful for like stock tracking. But in this problem, we want them horizontally because that's how I introduced the graphic. And then you're just going to hit compute, which will actually do all the work for us. And then it will produce a plot. It will produce the box plot. Okay, and then you just have to compare the picture that the StatCrunch produces to the options that they're giving you. And for this problem, for the numbers I have in mind, it turns out that the men's pulse rates will match up with D, and the women's pulse rates will match up with C. Now, it's kind of tricky on this because now they want us to compare these two box plots. Well, it's actually going to be easier when you do your StatCrunch because they'll be right above each other. So you can easily see, which one, are they spread out? Are they over the top of each other? So I have to kind of re-sketch the women one on the men one real quick. So the women one starts at around 55, so up here. Then the box starts at around 70, which is over here. The box goes to just almost 85. The median's at about 75 exactly. And then the upper whisker goes to 105. So just a quick dirty sketch. This is the men, this is the women. These are higher pulse rates as I go left to right. We already saw this. It's the same analysis we learned last time, but we saw it differently. What did we learn? Or should I say, what does this confirm that we learned in the last section? Women's pulse rates are generally higher. Does everyone see that? So this entire box is shifted to the right of the men box, which means generally women's pulse rates are higher than men. That's what this says. So to answer the question now, compare the box plots. In general, it appears that males have lower pulse rates. Oh yeah, that's true. So if you look at it from the male perspective, they're lower than females. The variation among the male pulse rates is similar to the variation among the... So this variation question is, how wide is this box compared to this one? And also, where is this middle line? Is it close to the middle or is it closer to one side or the other? Well, these are about the same. If you look at these two boxes alone, they look about the same. So that means their variation's about the same. So A actually says it perfectly. Men's are lower, but their variations, their boxes look pretty close. They're just shifted from each other. And then this is where I need to teach you how variation will show up with a box plot. So if we have a box plot that looks like this, and the middle bar is exactly in the middle, and the whiskers are about exactly the same length, this will translate to a normal curve that is exactly symmetric. So this bar will line up with the hump, and this will be symmetric. If we have a bar where the middle bar, this bar is way over here to the left, this middle bar tracks the hump. So my hump's going to be here, so it's going to be like that. I'd be impressed if you remember, what kind of curve did we call this? Skewed right. Does everyone remember that? Skewed right, because the tail is longer in the right. Okay, the last shape you can see would be if the middle bar is way to the right. Again, that tracks the hump of the normal curve. So it's going to go hump right there and then down. It has a much longer left tail, so we called that skewed left. But notice how it shows up in the box plot. So in the box plot, if this bar is in the middle, you have a symmetric bell curve. If this bar is way over to the left, you have a skewed right bell curve. So notice that's counterintuitive. And then if this bar, the middle bar, is way over to the right, you have a skewed left normal curve. So again, that makes box plots extremely useful because not only do you get the 5 numbers you care about, but you also can figure out the skewness of your normal curve just by looking at that middle bar. Okay, 29. When a data value is converted to a standardized scale representing the number of standard deviations the data value lies from the mean, we call the new value a, well, what's the new word we learned today and used a bunch? Z-score. Perfect. This is a Z-score. 30. In a modified box plot, a data value is a blank if it is above Q3 plus, oh, I forgot to tell you what IQR was. Ooh, that's bad on me. Shoot. All right, I can teach that real quick. In a box plot, let's just use a perfectly symmetrical one. Min, max, Q1, Q2 or median, Q3. This distance here is called IQR, or interquartile range. And it represents 50%, the middle 50% of data. And it's very easy to calculate. You take your Q3 number and you subtract Q1. So this is just a width. This is how wide is the box. Width of the box. This says to identify outliers is the answer here. To identify an outlier, you take the width of the box, you multiply by 1.5, and then you add that number to Q3. And any number bigger than that number will be an outlier. And it'll show up like this. There'll be little stars that are plotted past the maximum value. So these are called outliers. So notice this is tricky, because if you just take the biggest number in your data set and call it the max, that would be this outlier here. So what you actually have to do is first calculate IQR, multiply by 1.5, add that number to Q3, and then anything bigger than that are called outliers. And then the biggest number that remains when you don't consider these becomes your max. You can have outliers on both sides. You could have outliers over here too. So how that works is you take your IQR, your width of your box, times 1.5, and then you subtract that number from Q1. And any number that's smaller than that answer would be called outliers. And then once I don't consider those anymore, then the next smallest number is your minimum. So there's actually a little more work to these problems than I've shown you, because you'd have to do this outlier analysis every time. You can't necessarily just grab your smallest and grab your biggest and say min and max, because they might actually be outliers. Questions? That will conclude chapter 3.